All right. Good afternoon, everybody, and welcome at this Tech at Lunch organized by FlandersMake on the power of digital twins for design and operations. I'm Frank Naets. I'm from the FlandersMake at KULeuven core lab, the MMS. And so today I'm going to talk about digital twins, but more in particular about digital twins for high dynamic mechatronic systems. So everybody who wanted to see digital twins about stuff in the world, I'm sorry to disappoint you. We're just going to be talking about machines and high dynamic machines today. So over the past years, digital twins have become a very popular buzzword, so to say. It's a bit of a briefcase where different people fit different things into this. Now, I want to make it very clear what we're going to be talking about here today. And more in particular, we have this strategy within KULeuven where we're developing digital twins within the frame of an infinity cycle. And so this is what you can see here on the slide to my left. And so we see that what we're looking for is a way to bring together both the information that we have on digital assets and the information that we have available on physical assets. And so we don't just do this, let's say, on a modeling side in the early design stages, and we're not just looking at capturing data on a system that is already operational. We're looking for a way to bring together these two fields and combine all the information starting from the early design phases, making sure that we preserve everything that we know about a particular system all through the production and the manufacturing, where we can already see that variations can pop up in particular assets as a result of tolerances, as a result of deviations in the operation and in the manufacturing. And then finally, during the lifetime of the system, where we know that every system gets loaded in a different way, they undergo maybe different maintenances and so forth. And we want to bring in all this information. So bringing all the digital information we have initially together with the measurement information into a holistic framework. Now, doing this is a lot easier said than done, because it's not just about putting all this data together into a database and then saying, okay, now figure out what you want to do with it. In particular, we want to set up a framework that makes it relatively accessible for various engineers in order to exploit this information that's available from the model up to the final operation. And so in our case, when we're looking at these high dynamical mechanical systems, we're typically looking at multi-body models. And so for us, multi-body models, they allow us to actually start from the early CAD designs that are available, convert them into the model that we can handle, and then exploit them both for the analysis of the system, for the design of the system, and during the operation of the system. And so this is kind of what brings us together for these setups and the workflow that we have adopted. We have started from the CAD description. We converted this into a model for the original design. We could do various types of analysis there. We can update the model. We can make sure that the fidelity of the information we have increases and is more matched to the actual operation of the system. And then we exploit this in order to improve the design and go towards a final physical asset for which we can track the operational life cycle. Now, for these particular setups, we started from this setup to my right. And so in this setup on my right, what you see, it's a very classical linkage mechanism. And actually the initial design exercise we had was to improve the dynamic behavior by improving the design of the connecting rod. A simple enough exercise, and the final idea was we're going to reduce the vibrational levels. Now what we saw, and this was of course an idealization that we had as a result of the exercises we've done before based on the CAD, but not yet looking at the physical asset, was that we assumed that basically all the motion that was going to happen is going to happen in the parts of the linkage. Now, as most engineers who have worked on various mechanical designs probably know, that is, if you have a mechanism like this and it's turning at maybe 5, 10 revolutions per second, you might be okay. But if you're going to run this faster and faster, we will see increasing forces occur as a result of imbalances, especially as we look at this particular crank design. There is no balancing applied whatsoever. And so we see that very high vibrational levels pop up. And so here in this particular case, you even see that the vibrational levels are high enough such that this bearing housing visibly rotates or deforms back and forth as a result of the flexibility that is present in the mount. And so this is a particular challenge, as this flexibility that we have there, it's not part of the typical design functions that we're using. There is no spring attached there for which we can adjust the stiffness. And ideally, if our design was perfect, it wouldn't even be there. So we have a really hard time modeling this. So if we start from our initial CAD model and we construct our kind of idealized multi-body model, we would never see this flexibility. And so now we see this pop up, and the question is, how can we bring this into our digital twin framework such that the model we have actually represents the dynamic behavior that we're witnessing here. And to this end, once we convert our system into a multi-body model, we can actually start by applying some parameters to that stiffness, but in lack of better knowledge, these parameters can be very far off. And so, for example, you can get results, as you see here, with vastly exaggerated motions. And of course, now we can, on the one hand, we could try just saying trial and error, let's go by hand and update these parameters. That's a very tedious, very extensive exercise. But we know that we have accelerometer measurements present on the bearing housing, and that we can use this in order to improve those parameters. And so we've set up, starting from these models, an automatic optimization framework, which automatically looks for the best parameter set, such that the measurement that we get on this particular asset match as closely as possible to the model of this particular asset. So it's not necessarily a generic model for any of the systems that we're going to build, but it makes sure that for this particular case, we have the highest fidelity model possible. And so now we have a first version of our digital twin that we can start to exploit the next phase. So now we've gone through an initial kind of identification exercise. You can say in our infinity loop, we've gone back to the start. We can start thinking about design improvements. And in particular, the design improvement that we want to achieve here is in order to make the balancing of this system better. And how can we do this? Well, again, we start from exactly the same multi-body model, but now we say, well, we actually have more design freedom for this crank. And we know that a lot is caused and could potentially be solved by the crank design. And so we just know that the crank has to fit within the room that's available in the system. But basically, the design could be anything that fits within this circular shape, and that allows us to minimize the vibrations of the system. And so this is exactly what we've done. We took the same model as we used for the analyses. We extended the design space for the crank. So our digital twin lives on, and we started applying optimization, and more in particular, we started applying topology optimization. This is something fairly unique, what we can do with our tooling that we have developed at the DMMS. So this tooling allows us to run topology optimization fully coupled on these highly complex and dynamical systems. And so we can explicitly optimize in order to minimize the vibrations in the system. And so when we run this type of topology optimizations, we see that we get a design like this. So when we look here at this design, the blue space, that's basically the elements that can be removed. And the red space, that's the elements or the part of the material that we want to keep in order to minimize the vibrations. And so people who have ever looked at balanced cams, for example, will immediately recognize this type of design. The nice thing is now that in order to come to this design, this was not based on rule of thumbs for engineering. This was not based on a kind of ad hoc workflow in order to make the balancing better. No, we used exactly the same model as we used in the initial design, as we used for the initial identification in order to run this optimization. And all we had to do is not say, okay, we assume that there are particular rules of how you can balance the system. No, we just had to say, okay, we want to optimize the system such that the vibrations are minimized. And so this leads to a result like this. And for example, it's not as simple as just saying, I make the components as heavy as possible. And you immediately see that the optimizer itself says no, particular parts of the material should be removed in order to make the design more efficient. We also saw that, for example, if we change the type of material, we ended up with different designs, showing that the methodology really looks for the best possible solution for this system. And so then if we have a look at the behavior of this system, we see that when we run it at the same speeds, the vibrations are dramatically reduced. And so unfortunately, over the online system, you cannot hear it. Also, the noise levels have gone down dramatically. But so apart from the crank, all the rest of the design is exactly preserved. But as you see here, the housing of the bearing, it doesn't really move anymore. So we effectively reduce the vibration levels, which allows us to run the machine faster, which also reduces the loads on the various parts of the system, allowing us to increase the durability of the system. And so we have a very big win-win here in this particular situation. Now, the story of the digital twin doesn't end here yet. the next step is to say, okay, so now let's assume this system goes into commission. We still want to track what it's doing. There are still particular effects where we actually have very little knowledge and that we would like to know for if we go towards the third generation of the design. And so what we need for that are methods that allow us to take these models that are very powerful, but also relatively expensive. They're not nonlinear finite element expensive, but let's say that this type of optimization takes us a couple of hours to run. And what we say is we now have something such that we can process the data coming from the system in real time or near real time, such that we always have a perfect updating of what's going on in the system, and we can really take all the information, all the wealth of data that is being generated there. And a particular challenge is, of course, that for these kind of systems, we can apply some sensors, but we cannot apply sensors everywhere we want, and we cannot measure anything we want. So as you may have seen already, I'm not sure how clear it pops up on the video, but so for example, on the first setup, we also have an accelerometer mounted on the slider. Obviously, that's not ideal. You see there's a cable flying around there. So extracting that kind of information on moving components in mechanisms is extremely challenging. And so very often the cost of the sensors basically completely eliminates the benefit of what you would like to see on the real system, just because it's so excessive. And so what we can do in those cases is we can take that exact same multi-body model again that we used for the design, that we used for the updating, that we used for the optimization, and compress that into a much smaller model through model order reduction methods. And these model order reduction methods allow these models to be run in real time on this relatively ancient D-space system that we have available here, such that we can constantly extract the parameters and the state of the system. So for example, here you see the estimation running as it runs in real time on the system, and we generate data like the angle of the system, the velocity of the system, but we can also extract all the other data that's available inside a model like this, and that's really the wealth there. So normally if we take sensors, basically the amount of information we have scales directly with the number of sensors we have. If we exploit these models together with measurement data in a virtual sensing setting, we can dramatically increase the amount of information that becomes available. And for example, we can track throughout the operation of the system the corrective force that is applied, which we didn't account for in the model as a result of friction in all the various components. And for example, mismatches on the inertia, as you see here on the far left side of the figure. And so this generation of information, this wealth of data that we have available, that's really the strength of the digital twin paradigm. So where in a classical approach, we had to kind of take step-by-step approaches in order to tackle every stage of the life cycle. We had to have particular methods for the design. We had particular methods in identification. We had particular methods in optimization and for state estimation. We now see that through these new approaches, we managed to bring all of this together to a single framework. And especially when we're talking about mechanisms, flexible multi-body is basically the fundamental vehicle that allows us to do that. So it allows us to bring all this information together, scale up and down in the level of complexity, looking more at the general motion of the system towards the very fine stress concentrations that occur as a result of the motion of the system, and allow the engineers to basically seamlessly transition through every phase of the product in order to bring to life these digital twins and extract information that allows us to effectively speed up the mechanisms which we had before, increasing the durability of the system, providing better control, and so forth. And so hereby, I would like to thank you for your attention and for your attendance. Normally, and I forgot to mention this at the beginning of my presentation, but so there's a Q&A window. So if you have any questions, unfortunately, we cannot unmute you, but if you type your questions there, I can respond to them. At this moment, there are no questions yet, but so we can give you a couple of minutes to see if any pop up. And of course, in the future, if you would come up with questions, you can always contact us as well. I don't see it yet. Let me see. I get live event hasn't started yet. It's presumably a glitch. No, yes, so this is something that actually we developed over the past 3 years. So the question was, is the topology integrated? So there are methods already around for a couple of years that actually allow you to run a multi-body simulation, take out the results, for example, the forces on a component, and then perform a separate topology optimization. The problem that you have is it allows you to minimize the stress in that particular component with respect to the loads on that particular component, but it doesn't allow you to do something like what we did here, where actually we said we want to optimize the design of the crank in order to minimize the deformation in the bearing housing. So this is something that classically was not possible. We have set up a completely integrated framework that allows us to do this. This is actually implemented in a very general design framework, so we can do this for any kind of mechanism that we can model through multi-body simulation. And we're very flexible there with the types of design requirements that we account for. Yeah. So the question was, if you haven't heard, so how we determine the initial conditions for the digital twin. There's a number of approaches to that, and also on how you define initial conditions. So we always kind of start from doing a more extensive measurement on the system. And so we assume, for starters, that actually our nominal design, so what comes out of the CAD, is indeed in good correspondence to what the real system will be. And then we will determine what are the main parameters where we expect to see deviations. And so for us, in this case, just even visually looking at the mechanism, we saw that indeed this deformation of the bearing housing was something that we didn't account for and that we had to add to the model. The initial stiffness we selected there, that's always a bit of a challenge. So we kind of just threw a number at it. And we did see, of course, as we're using gradient-based optimization in order to find the right parameters, that the more accurate we were with our initial guess, the easier the algorithms ran. We also played around a bit with, for example, doing the identification in the frequency domain or in the time domain. Both can have a different influence on how identifiable particular quantities are. But so this is definitely a challenge to kind of find out what's the best starting points, especially when we're looking at more complex phenomena that are not directly related to the geometry, like these stiffnesses, like damping in the components, like friction in the components. So currently it's a bit of a trial and error still in order to come up with the initial guesses that then give us a somewhat decent convergence towards the real good results. Yeah, so the question is basically, what do we have to do if the load changes? So I think this is a really good question. This is something where we're currently kind of just starting to explore it. And for maybe some of you, we are currently preparing a project proposal called DEMOCO, an SBO project, where we're actually trying to tackle one of those questions in detail. So currently there is a bit of a mismatch there. If you look at various applications, we know in the initial design that our system will be used for different purposes, and in most applications we don't really know how or what the realistic load cycles will be, or we're not really capable of assessing what then the most critical load cycles will be. This is typically seen also in automotive, where classically for durability, brands are really good at developing durable cars for the European market, but that doesn't mean that they have the same load cycles as what they would see, for example, in an Asian or in an African market. And so we're trying to set up these schemes, and in particular these state estimation schemes, such that we can actually take the operational data of the system, extract representative load cases, and send this back to the initial design stages. There, it's not just about saying how fast systems will run, but for example, the forces that are acting on the system. That's something that's really difficult to measure directly. We're trying to use these schemes in order to measure that indirectly, such that that information becomes available for the design engineers. Normally, the way that we approach it is the digital twin should be insensitive towards the load cycle, but very often there are different types of aspects, like indeed friction and damping, that do have some dependency on the load cycle. And so we actually expect to learn a lot there in the upcoming years when we start to implement these methods more and more. So the question is, what do we need to change about our models if we want to basically make them applicable towards this entire design cycle? And actually, this is something, well, basically, we need to be able to implement the models in our internal flexible multi-body toolbox. Now, currently, we can handle more or less all types of multi-body models that can be handled in commercial software. So that's only a vague limitation. And basically what we did over the past years, also in various FlandersMake projects, is actually set up the tooling so that we can automatically convert the models through these various stages. So basically when we define a component in one of these multi-body models, initially we might just say, okay, it's a component with known parameters. Afterwards, it's basically a toggle of a switch where we can say, okay, now there are some of the parameters in the model that are unknown, and that allows us to actually run the optimization engine. And then finally, if we want to go towards the state estimation, it's actually an additional toolbox that takes the initial model and converts it into a real-time capable model, which we can use for state estimation. So again, here the focus is really to minimize the friction that you have from the engineering perspective, and really build upon this numerical tool chain that exists, but very often is not coupled together. All right, I think we've gone through all our questions. So I thank you all for attending. And if there are any other requests or interests, feel free to let us know. We'd be very happy to collaborate on these topics in the future with you.